And so what we would like to do is essentially, I would like to do two things, okay? One is to finish the story about structure sparsity in the case of just consider simple linear models. And if you remember, what we were left with is looking a bit more carefully in the case where you have variables divided in groups, but the groups are, remember? You have variables divided in groups, but our groups are not just are not nice groups in general, but they could be overlapping, okay? So we need to look a bit into that, how you deal with that situation. And then we're going to spend actually some time going beyond the linear models and introduce multiple kernel learning, okay? We're somewhat going to bridge the kernel methods we have seen in the first few lectures with the sparsity idea we've seen in the last three, introducing a class of methods that tend to help, try to merge these two ideas in some fairly natural way, I would say. Okay, so group lasso without overlap and multiple kernel learning are the two topics we would like to cover today. So let me just recap what we need from what you've seen so far. So the idea is, as usual, that from data we define some empirical error, and then we look at some form of penalized regularization. So we're looking at linear models here. So our function just looks like this, okay? So we are effectively replacing function with the parameterization, which are vector in RD. Now, the story so far went like this, okay? We started arguing that if sparsity is our goal, that it's finding function for which only some of the coefficients are different from zero, the zero norm will be somewhat the ideal modeling solution. Turns out that this one here is actually not feasible from a practical perspective, and so we thought about replacing this with L1, which can be seen as literally a convex relaxation. Okay, it's a convex function that gives you an upper bound on this function here. And then we discussed two things. We tried to convince ourselves that indeed this W1 gives me something sparse. And we did this by, on the one hand, introducing, say, what I call the ISTA, the iterative soft thresholding algorithm, a special instance of the general scheme of proximal forward-backward splitting approaches to convex but non-smooth optimization. Do you remember how ISTA looks like? It's an iterative procedure to compute the minimizer of this in the case where R is the L1 norm. How does it look like? How does the iteration look like? Do you remember? It feels a bit like a projected gradient. So projected gradient would just be take a step of you have a set of constraints, take a step of the gradient, and then project the coefficients you found on the constraint set. In this case, it's not quite a projection in general. It depends on the form of R. In the case of L1, can be related to a projection, but easy to see as a soft thresholding operator. Okay, the general object you need at each iteration is what you call the proximal operator. Okay, we gave the definition, discussed quite a bit in detail what it is. But in particular case of L1, the proximal operator is a nonlinear map that reduces to a much simpler operation that we call soft thresholding. You remember how the soft thresholding works? So at each step, you take a step of the gradient, you return a vector, then what do?
Check it with the question, and then you either zero it out.
You go and look in component-wise. You look at each component. If the component is small, you zero it out. If it's big, you don't let it go. You don't let it be as it is. But if it's bigger enough, you decrease it a bit, and if it's smaller enough, you increase it a little bit. So you introduce a little bias. Okay? And last time we spent quite a bit of time discussing essentially some tricks that can be used to alleviate potential bias introduced by this operation. Okay? Let me just try to say one thing that I noticed that I was struggling communicating, and perhaps after class, by answering some question, I had the feeling that perhaps I was explaining a bit better. So if you remember, this was the story where I said, oh, you should use L1 or L1 plus least squares. Okay? Do you remember more or less the story? So the scheme one is just you fix, again, you have a box, which is L1. You enter the data and the lambda, and you return a vector. Okay? And for each lambda, you can go in and check, say, the zero norm of this vector. It will be a certain number. And just as a sanity check, how do you think this number is going to depend on lambda? If lambda is big or small, this is going to be smaller or bigger?
Lambda is big, that's smaller.
Yeah. So if lambda is big, then a lot of this stuff is going to be 0. So this, a lot of the coefficients are going to be 0. So this is going to be a very small number. Okay? Okay, fair enough. So the idea is, on the one hand, okay, you know, this is just a regularization parameter. You're going to have to choose it in some way. Use this algorithm by checking different lambdas and computing different solutions. Okay? And my point the other time was just, yes, you can do that, but the problem is that in practice what you see is that the bias, you pay the bias you introduce to make computation nice, and the coefficients you are estimating can be slightly off. Okay? And so people propose a different procedure that essentially replaces this box with another box, which is L1 plus OLS, okay, on selected variables. So what do I mean by this? Fix a lambda, okay, compute L1, go in, check the solutions, okay, check the solution that is returned by this guy. You can go and check what is the support, okay, that is the J such that, so which J are the coefficients returned by L1 are different from 0, okay? And now you can just solve this problem. So take the data matrix, remove all the columns which are not in the support, all the variables which are not being selected at this step, and recompute the coefficients. Okay? So this is my new box, okay? Instead of using this box, I want to use this L1 plus OLX box. So essentially I say, I trust this method to select the right variable, but I don't trust the way it computes the coefficients. Okay? So far so good? So up to now we have two algorithms to do things. Algorithm 1, pure L1, and algorithm 2, which is L1 plus OLS. Okay? I don't think this part is the one that is hard to understand because these are just two procedures. Okay? The comment that I made that seemed to create a bit of confusion when I said that by using the second scheme, this one, you can actually find solutions that are as good as the first scheme but sparser. So they would give you the same prediction accuracy but will be sparser. Okay? I think this was the comment I made that seemed to create a bit of confusion. And I think perhaps the confusion came from the fact that by this I don't mean that this OLS is not going to further reduce the set S in any way. Okay? OLS is not going to reduce the set S in any way. If you're given these many variables, once you solve these squares, you're going to have exactly that many variables. Okay, that's not the point. The point is just that you recompute the coefficients. Okay? So far so good? Suppose that now you have two lambdas, okay? You have one lambda here, which is bigger than another lambda here, which is smaller. Okay? Then you can compute, let's give a name to this solution, okay? How shall we call it? Well, let me call it, so it depends on lambda, because if you want this set, depends on lambda. Okay, so if I fix a lambda, I obtain a set, and then I solve this. But it's not this one here, so let me just put another, I put a tilde rather than a hat. Okay? So for each lambda, now I can compute two solutions if you want. I can compute the solution of the pure L1, the one that I call with a hat, of the solution of the L1 plus OLS, which is the one that I denote by W tilde. So my point here is that by doing this, rather than this, you can allow yourself perhaps a bigger lambda. Why? Because bigger lambda means more sparse, but this algorithm recompute the coefficients, okay? And by doing that, it can actually get, a fewer, in some sense, what I'm saying is, a fewer number of coefficients with the right weight can do as well as a larger number of coefficients with the wrong weights, okay? Or the slightly, not wrong, but slightly off weights, okay? So this is what is meant to say. I'm trying to compute better the coefficients to check if a smaller number can be good enough. And this is what this procedure supposedly might allow you to do, okay? In practice, at least in all the statistical scenario I know, it is hardly ever the case that one uses L1 alone, but typically you use this two-step procedure every time. Notice that in some sense the idea here is if I would know which variables are important, I could just do OLS on those ones. I don't know it. So what I do is that I use L1 as a selector and OLS as a computation of coefficients, rather than try to do both steps at once. Okay. I'm not going to try one more time because I already feel frustrated now, but if you have any questions here, I'm happy to answer. Does it make a bit more sense than last time? It's impossible because already last time probably was perfect, but suppose a contradiction that it was not. Okay, anyway. So, fair enough. So this was one comment how you use this in practice and the effect of the bias. Then there is this story that aside from computation, you can try to convince yourself that also from the modeling perspective, the convex relaxation is one way to go. And to do this, last time we gave this geometric aspect, which was basically related to thinking a bit about how the L1 ball interact with this possible space of solution. Okay, and convince yourself that in the case of the L1 ball, typically in this simple two-dimensional case, the touching point of those two curves will be a sparse vector, either in the vertical or the horizontal axis. Okay, and I feel that this is more or less synced in. There was a question about what happened in higher dimension. Okay, and I guess the short answer, even after checking a bit more, is that it's not easy to see because you really have to go in. You have to think of a very high-dimensional situation. And if you look, basically, the results, the mathematical justification of this relies on actually some fairly deep result, okay, in geometric functional analysis and high-dimensional probability. Particularly, I think a clean answer is given by so-called Gordon theorem. Okay, there is a nice paper by Ben Recht, Pablo Parillo, Wilski, and Chandrasekaran of a couple of years ago that I somewhat give a nice answer. Thinking back of like a couple of people had the intuition that if you go in high dimension, you might still hit only corners where there is just one component different from zero. This was what created the question. But now thinking back at the question, it's actually not that natural to think that that's going to be the most likely situation. First of all, because when you go in higher dimension, suppose, for example, that now this thing is three-dimensional. Okay. Now, this can be a plane, but this can also be a line, right? It all depends on the amount of correlation in your data, the amount, or if you want the number of rows and columns. So if you now take, for example, a line, it's not so unlikely that it's going to actually touch an edge, okay? Because there are a lot of edges. Essentially, while a face is just one direction, there are going to be all these, even for the planes, there are going to be all these different directions, all the different planes you can get. They're actually going to touch this in this direction. If you consider this to be a two-dimensional set. Even more, if you consider it to be a one-dimensional set, you can convince yourself perhaps even more. But again, these are intuition that we're trying to build in high dimension, so I'm not sure how much we share the same intuition here. But at least to me, the idea that if you take a line, and now you try to see where you touch this diamond, it will be not only in the tips, but also, for example, in the edges, is actually not that unintuitive. I think it's quite intuitive that that will happen quite often. And essentially, the theorem gives you quantifies exactly the probability that a hyperplane is going to touch in the way in which the probability that a hyperplane is going to touch this polyhedron set in a vector of a certain sparsity level. Okay. So again, this is my attempt to just give a little bit of intuition, of responding of an intuition with another intuition. The theorem itself is actually the proof itself is actually not horribly complicated, but it's technical and using notions that are beyond our interest here. So what we did last time after this is saying, okay, if I have correlation, meaning if the columns that correspond to variables that are important tend to be very aligned, a comment that somebody made, which is correct, you think of the column to be unit norm, so that there is no spurious weighting inside of the weights because of just resizing of the column size. Then an idea is to replace the L1 norm with let's see how I wrote it. With this kind of convex combination between L1 and L2 norm, which is what we call elastic net. Do you remember roughly what was the intuition behind this penalty? We actually said a lot of stuff about this penalty, but you remember some? Right. So on the one hand, this term enforces uniqueness of the solution. Okay. But if you only take this, the same drawing that we did for the L1 convinced us that the L2 alone might not be sparse. Whereas this one here is the purely sparse one. So in some sense here, by picking alpha, we are making a trade-off between the stability in the sense of uniqueness of the solution and the fact of obtaining sparsity. That's definitely the point. Remember something else? The other comment that I remember is somewhat what led the way to the next point, which was talking about structure sparsity. Okay, which is the case when you know further structure that isn't contained in your data, in your variables, for example, group structure. If you remember, we commented on the fact that there is some grouping going on when you use this. Somebody remembers why?
If distributed family among variables, that's how I
Exactly. So what he just said is that this algorithm, if you have two or more variables that are correlated, because of uniqueness, is going to share the weight among those variables equally. And so if you have more than one variable that is important, that is important but correlated, rather than picking just one, you're actually going to try to pick them all up by putting the same weights on each of them. And this gives some kind of grouping property of the algorithm. And we commented that the problem of this is that you actually don't know how to, in practical numerical, you don't know how to recognize the groups. Okay, and that's, as far as I know, is an open problem. To exploit the group structure in the data points, but also to detect the group structure in the data. Okay? But these already point us to situations that are beyond the pure L1, where you might have some kind of further structure in your variable. Okay, that's what elastic net proposes to do. And this, launches the idea of looking at structure sparsity, which is a general term for ideas that are in line with L1, but with more prior information, rather than just to know that some entries of the vector are 0, I know something more. And one such case is the simplest one, is what is sometimes called the group lasso. Okay. I don't know if you ever used the word lasso so far. I mean, maybe last time, but just in passing. So this is just overlooked. So historically, L1 norm has been used by practitioners since forever. But at some point, it was really advertised in the mid-90s, pretty much, and pretty much around the same time in statistics and in signal processing. In statistics, the running name has mostly been this one here, which is an acronym for something, but I don't remember. So anybody remembers? It's at least, I think it starts with least. Yeah. Okay. Yeah. So it's one of those, and the name in signal processing is typically basis pursuit, because the idea there is to some extent that this is really, if you want the variable selection point of view, you're going to select. In basis pursuit, typically the idea is that first of all you define a bunch of features, which can be a redundant set containing many bases and many different elements. And then what you do is that you try to you select the bases that are important. So in that sense, it's a basis pursuit, okay? I guess Shirani is the person attached to this name, whereas Donahoe, Saunders, and Chen, I think, are the three authors of the basis pursuit paper. Then Donahoe have been working a lot on this in subsequent papers. So here we want to look at the so-called group lasso extension of the lasso algorithm. Do you remember how this looks like? We're going to start with a simple case where there are groups with no overlap. Okay. Let's write it here. Group lasso, no overlap. Do you remember how the algorithm looked like? It's always of the same form. It's empirical error plus penalty. But the penalty now is based on knowledge of group structure in the variables. Anybody remembers how? So you have a vector W, which is in RD, okay? And now you're going to disintegrate it in 1 up to G components, where each of these components, Wj, belongs to, say, Rdj, j from 1 to G, okay? So you're basically saying that you have a vector, and now you split it in, say, 3 parts, if G is equal to 3, that are not overlapping, and I call W1, W2, W3 these pieces. The assumption now is that this group structure is given a priori. Of course, they don't have to be adjacent, okay? And this is just to draw it in a simple way. And provided with this notation, the idea is that we're going to define R exactly as our colleague recalled us, which is the sum over the groups of the norms of the pieces, okay? And somebody last time said that, felt like calling this an L1, L2 norm. Because what you're doing is that you take the vector, you compute the L2 norm of each of these pieces, and then of the vector of norms you obtain, you take the L1 norm. Okay? So in some sense, that not only us, but a lot of people call this an L1, L2 norm. Notice that this is not the usual ridge regression, because we don't put here the square. Okay? Also notice that here, essentially, because you demanded it, I dropped the exact notion of norm I'm using. What I mean is that if you want, strictly speaking, this is going to be RDJ, just the Euclidean norm in the space with the right size, okay? Because each of these vectors will belong to a different group, but in general, they don't have the same size, okay? Now, already this one gives an intuition that because you can see that of an L1, L2 norm, the idea here is that the L1 nature of the penalty is going to try to suppress not individual variables, but groups of variables that are somewhat kept together by the fact that I take their norms. That's somewhat the intuition of this penalty here. And the intuition is made even more explicit if we consider the Prox operator. It turns out to be possible to define it not component-wise, or depending on what you call a component, but like piece-wise, group-wise. Somebody remember how this guy is defined? So you take a vector, you're going to look at, say, a piece, the Wj piece, and then what do? You're going to check if the norm of that piece, not a component, but the norm of that piece, is big or small than lambda. And then what do you do? If it's small, zeroes it out. If it's big, well, again, in principle, you just would like to keep the vector. But what you really do is that you actually subtract this quantity. Okay? If you assume that the group are dimension 1, each of them is dimension 1, this is simply L1 minimization. Okay? So this is just a... Yep. I think this should be... Okay? And this is another way to see that this, in some sense, the algorithm that is going to compute the solution of this problem with this penalty is going to have inside at each step a projection, actually a proximal mapping, that is basically zeroing out a whole set of coefficients that give rise to a norm smaller than lambda. Okay? All right, so this is more or less where we're at. So the next step is, what if, in some sense, my grouping structure is overlapping. So this is group 1, this is group 2, and this is group 3. So in this case, well, let's see. Okay, there are two things, I guess, to say. One is, we made a couple of comments, okay? We just came short of actually defining the algorithm. If you have overlapping groups, you can make at least two choices. We ask this question and we provide an answer. So you have to decide how you want to treat the overlaps, okay? Suppose that I give you this algorithm and you simply apply it as it is to this set. What would you do? How would you treat the overlaps? Suppose that you just, in this case, and suppose that the norm of these two pieces is small. What variables would you select? So you take all this and you set it equal to 0. You take all this and you set it equal to 0. And all you're left with is this guy, which is not a group. It's all that is left of a group after you took off the other stuff. It's a complement of a group, if you want. Okay? So if you just go in and apply that scheme to overlapping groups, you're not working with groups, but with the complement of the groups. Okay? So far, so good? So the next question is, and this might be interesting in some situation, but the next question is, okay, what would you do if you actually want to keep the group structure? Group. Oh.
You could do this for selection and then do ordinary least squares on the groups that have parts that are left over.
So I'm going to select this.
Right, so you'd select the green
Suppose
guy,
that you do in this case, so I just select this guy. And then what would you do?
and then you would redo the problem with just regular least squares.
On those.
Yeah.
But you still have lost everything in the same group, which has not been selected.
Well, you would keep the things in the group. So you'd keep
The one that are selected. So I guess my question is, suppose that I really care about this, okay? So what I really want to do is, even in the overlapping case, to select groups. Here I'm discarding groups, and by discarding groups, I'm selecting complement of groups. But suppose that what I really want to do is select groups, okay? So I want to discard complement of groups. So if I do what you're saying, I will still be left with what I left, with what I selected, which is not the whole group, but a piece.
Would you select like the union of all the groups that intersect with what you have left?
The union.
Like if any group intersects with what you have left, you select the whole group.
Maybe. Yeah, maybe it works. So I think that might actually work. So another way of doing this, okay, which is what we want to show now, is kind of a bit brutal, okay, and it's going to be the following. Take the variables that are in the overlaps and replicate them, okay? So in some sense, you take this vector, and in some sense, you artificially make it non-overlapping. Okay, so here just put a little space, but it's not there. So literally what I have to do is that when I have a variable in an overlap, in my data, I have to repeat it. A column in the data, I need to repeat it twice, okay? If you do that, when you go in and discard a group, there's going to be another, the other group is going to be fully written on a new set of variables, which overlap with the first one, but you don't care. So if you destroy these two, you're still going to have this, okay? What do you think is the bottleneck of this procedure? That's actually fine, right? You could do this. Do you have any shortcoming in doing this, you think?
Two are surviving both copies. So first group and second group
Yeah,
surviving, and then
but it's okay. I wanted to select group, so that's okay, right? I'm thinking of something computational. Yeah.
If there's like almost everything overlaps, then you like duplicate.
A lot of stuff.
Yeah.
Yeah, so that's one thing I have in mind. There might be some others. If this, suppose that you have an overlap of roughly 50%, okay, then you're going to augment the size of your data a lot, artificially. It's not there. So if you have a matrix which is, say, I don't know, 1,000 by 50,000, you might make it much, much, much larger than 50,000 by adding a lot of artificial columns. So this approach might fall short in giving you what you want, okay? The short answer to this is that, well, unfortunately, you will have to change this approach a little bit. But let me, before discussing that, let's just try to write down this simple idea, okay, in a very complicated way. So suppose that I give you the following, okay? Groups are overlapping, and now I'm going to define the following penalty. Is the minimum of exactly the so is the minimum of that stuff, okay? But the problem is now my vector overlap. So before, if I give you a vector W, there was a unique way of writing it in pieces, right? Because they don't overlap. But because now overlap, think of here, if I give you a W, and suppose now you have to do W1, W2, okay, the two pieces. You don't have a single way of doing it. You have many possible ways. For example, you could say that W1 has non-zero up to here, and then is 0 in the rest. Or you can do the opposite with W2, okay? So in the overlap, you have many possible, infinitely many ways to realize the same vector by overlapping the two shorter vectors. Do you agree? Is that correct? Again, suppose that I give you this vector W. Suppose that I want to split it in two, okay, in the middle. There is only one way of doing it. But suppose that now I want to do a split. So I have a group that is the first 2/3, and I have a group that is the second 2/3. Then there is a big 1/3 overlap in the middle. And now you can decide what you can define many different W's that summed up, that concatenated is going to give you the same W. Okay? You can decide, for example, one is going to be, for example, say W1, W2, 0, 0, 0, 0, 0, and the other is going to be 0, 0. So I can choose this to be my W1, and then this one to be W2, the rest. Okay? Or what I can do, for example, is to say W1 to be W1, W2, W3, and then just put an extra 0 here. So I have many possible ways to combine the two vectors to give me the same result. So to define a well-defined functional here, actually a norm, among all the possible ways you have to disintegrate the vector W in pieces. You want to take the one that gives you the smallest norm. So you take, and I need a little bit of notation. If you want a better notation, is this. So I have to tell you what is Wj, okay? Suppose that I give you a vector Wj in Rdj, okay? So it's a vector which is short. What is the W bar version? It's essentially what I did here. So it's the one where I make it long. So it's going to be in Rd, which is the size of W, okay? And what I did is that I kept the entries corresponding to this guy, and I put zeros in all the others, okay? If I do that, so suppose that I have W1, which is this small piece, W2, which is the other piece. I take their bar version, which is, I just make them as long as the original vector, so that now if I sum these two long vector, I'm exactly trying to reconstruct the first one. Okay? So it's just another way to say that, in some sense, I want to concatenate and overlap the two vectors. Yep.
What's the norm inside the curly vectors?
This one,
Yeah.
same as there. So this would be R, D, J. It's the same as before, but essentially I'm saying because now I have multiple ways to write my vectors, among all the possible way to disintegrate a vector in pieces, keep the one that is going to give me the smallest norm. Okay? And this is just a notation to tell you, to put the fact that these pieces should be giving you back exactly the original vector.
Yeah, I was thinking that it's possible that, here you have W3 being either 0 or something positive. Is it possible that it's going to be positive in both groups?
Say it again.
This is
You could.
You could?
Yeah, I think so.
Because it's including a norm, I don't think.
Yeah, I think you could, but that won't be a problem. Is this expression clear? So again, the key point here is that I have multiple ways to disintegrate my vectors in parts, and among all the possible ways to do it, I want to take the one with minimal norm. Okay? And this is going to define the penalty I want to use. Yeah?
Will the one with minimal norm be where you split the overlap exactly in half between the two vectors?
No, I don't think.
Like you divide the
Yeah, I see what you're saying.
overlapping part by two.
If the overlap is if they're same, yeah, maybe. No, but I guess no. I'm not sure. I have to think about it. I have to think about it. Maybe. So, sorry? Absolutely, yes. You can have very complicated overlap. That's why I have to think a second about it also, because it depends on the coefficient, the size of the groups. I'm not sure. My intuition that maybe yes, but I have to think a second of specific cases. Okay. Anyway, so this is just to convince you that in the case of groups with overlap, you have to do something because you have too many. If you just do this, you have multiple ways to define the norm. Okay. What I want to convince you next is that if you use this norm in that algorithm just as a penalty, you get exactly the algorithm that we described that is virtually replicating the variables. Okay? So the thing that we describe intuitively as, oh, give me just the old algorithm, but artificially replicate variable, turns out to be equivalent to actually keep the number of variables that you actually have fixed without any replication and using this expression here. Okay? So that's what we want to do next. So this is, let me call it group lasso with overlap. Okay, GLO. So what I want to show is that if you take the minimum over W of this plus lambda R GLO W, okay, I want to try to show you that it's actually equivalent to the scheme where you actually use the usual norm and you replicate it. So not the usual, the basic group lasso with no overlap norm, but replicate the variables. How do you think we can do this? So the idea is essentially that you see in the definition of this group lasso with overlap norm, there is a minimum. What I want to do is to put it in front of everything. Okay? So now I just rewrote it, okay? Instead of writing it in this form, I just wrote it like this. So it's the minimum of the sum of norms over W1, WG, such that their sum is going to give you W, okay? I just rewrote that in here. What I want to do now is to take this and put it in front, okay? So what you have is that you get equivalent to the minimum over W of the minimum over W1 in RD1, WG in RDG, such that sum Wj equal W. Okay? E hat W plus lambda sum Wj Rdj j from 1 to g. Okay? I just put it in front. The first, this guy here doesn't depend on W1, WG, so I can just put the minimization in front. But now look at this. By this assumption, W is exactly equal to this stuff, right? So what I can do is that I can just rewrite this as E hat of sum Wj plus lambda sum Wj, j from 1 to g. And here I have to put the minimum. Okay? So notice what I did here is just that I said, oh, this W is exactly equal to the sum. So let me just put here, instead of W, the sum. Okay? And now I should have still these two minimization. 1 over W, 1 over all this sequence. But where is W appearing? So I can do it now. There's a 1 over W, and then the 1 over W1, WG, such that they sum up to W. Okay? But W doesn't appear here anymore. It only appears here. And so in some sense, the minimization over W here is redundant, because I'm minimizing all the individual addend of that sum. So I'm also minimizing the sum. So what you can do is that you can literally drop this. Okay? So far so good? So the steps are, you write down the problem just with the regularization that I wrote above. Then, this is mostly for pedagogical reason, I rewrite exactly what I wrote, okay, with this minimum appearing here. So I did nothing. But then I do something, which is I move this minimization in front, and I can do it. Then I realize that I can just replace W with this symbol, because by definition of my problem it's true. And then at that point I realize that the minimization over W is redundant, okay? And I get this new problem. The two problems are equivalent, completely equivalent. We're not there yet. We need to take one more step to realize what the heck we're doing, okay? So look at this now. Any questions about this? This is just a couple of technical steps, okay? I mean, if you think about it a couple of times, there's no particular, there's nothing particularly conceptual about it. But now look at this. If you look at this, you're going to have some loss function that depend on, evaluated on the point, where this guy here is going to be what? It's just going to be W bar J xi. Okay? So this f xi is just going to be a linear function with coefficient given by this. But then it means that I can put this inside. And if you think about it, what you're actually doing now is that every time you multiply this vector times x, you're zeroing out all the components that are outside of groups. Okay? So you have x1 gets multiplied by, say, the first vector. And basically, this is equivalent to zeroing out all those components and keeping only the first few. Then you're going to say the second vector. And then you're going to multiply and keep only this. But then it means that you're replicated this variable. Okay? So you can convince yourself that by using this expression, if you try to write it now in vector notation, what you could do is basically to take this vector of w and concatenate it in a very large vector. And all these x's obtained by zeroing out what's not in the different groups and just obtaining this augmented matrix. Okay? So, as promised, this is the complicated way to do what heuristically we thought, which was simply replicate the variables. Okay? Or if you want, jokes apart, it shows that this replication strategy actually corresponds to this kind of technique based on essentially solving the overlap in a somewhat principled way. Okay? So again, this is a little calculation that you can just look at again, but there is nothing tricky in it.
Sorry.
Yes?
In the minimization, do we still need that the sum of w are equal to w? I don't think that's necessary.
Yes, sorry, this one. Absolutely. Yeah. I basically remove both the condition on w. I parameterize instead of with w, I parameterize with w1, wg, and that's it. Okay? Yep, very good. So notice that if you just have this heuristic argument of the idea of replicating, you don't know that this is equivalent of doing this. So we learned something. We learned that this is equivalent to using this penalty. And now back to our main complaint, which was that we don't have the that we had to replicate variables. You could ask, oh, is there a way to compute the prox operator of this? Yes, you could. You can equivalently phrase this problem this way, and then just do replication and use that prox operator. But that's just artificial in a way. Can you directly compute the prox of this? Does the question make sense? And the answer is almost, in the sense that it's one of those cases where you can compute it but not in closed form. Okay? So you have to run an inner iteration, which turns out to be a sequence of projections, so it's actually not bad. So you can compute it with a certain level of precision. But the prox operator associated to this will not just have a simple block thresholding operator. It's one of the situations where you do have to somewhat do extra computations. So in some sense, the price here, depending on the amount of overlap you have, is either you pay memory, and you use the simple block thresholding, or if you don't want to pay memory, you are going to pay time. Okay? Keep the memory the same, but then having to run an inner loop iteration in your proximal forward backward splitting operation. Okay? Okay, so just to wrap up this part of the lecture before moving to multiple kernel learning, let me make a few comments. Okay? One comment is that this is just a starting point, okay? And one way to generalize this, depending on the problem you have, is, for example, take here something like a LQ norm, which will basically mean that here you have to take LQ, and here you have to take P and 1 over P, okay? LQ is defined the same way with the components. Why would you want to do that? Well, because again, these correspond, if you want, in other terms, correspond to priors. Okay, depending on different priors you might have the vectors, you might want to use different norms. Okay, we used L1, L2 with this idea that we wanted to select groups, but you can invent, depending on the problem at hand. As in the kernel methods case, the art was in the way you build the kernel. Here is oftentimes in the way you design these penalties to reflect their prior knowledge. Okay? So another thing you might have, and this I'm just going to give a quick hint, is a case where rather than having this kind of flat structure in the groups, you know something more. So you have overlap, but you know, for example, that there is a big group which contains all the groups. And then you split, say you have a tree, for example. You know that groups are divided in parents that are divided in parents and so on and so forth. Or you might have a graph structure on the groups, okay? And then you can ask, if I give you the graph structure or the tree structure, can you design penalties in such a way to respect the tree or graph structure? And the answer is yes, okay? Of course, you know, what you might pay is that at that point the number of groups grows exponentially. And people have been not only looking at a way to incorporate this information, but also a way to somewhat simplify the computation in the case you make some assumption. For example, you say, if a parent doesn't appear, then also the leaf, you know, the child won't appear. So in some sense, you know, assumption like this might help you reduce the computation, because instead of having to visit any node in a tree, you can just, you know, chop off large parts of it by making assumption like, you know, if this parent doesn't appear, I'm not going to bother go down there. Okay, so this couple of remarks is just to tell you that this is just the, you know, the tip of the iceberg, and there is a lot of further manipulation you can do to the penalty, so that you can incorporate more prior information, either in the form of changing the norms or in the form of incorporating further group information about the groups beyond just pure the overlap or not. Okay. Now, what we would like to do in this last half an hour is something that for a while is just going to look like a change of notation. Okay? So I'm going to try to do it a bit fast, and you should interrupt me if you get lost, because the change of notation is mostly boring, and then it will mean something. Okay? And when we finish changing notation, we realize, oh, wait, we get something different from what we started from. Okay? So basically what I want to do is view what I call the disintegration of a vector into its parts as a sequence of feature maps applied on the vector. Okay? And then from feature maps, I'm going to define some kernels, and then I'm going to bridge. At some point, I'm just going to rewrite the group lasso. So we want to go from the group lasso to what is called MKL, multiple kernel learning. The problem of learning not with one, but with many kernels. Okay? And at the beginning, what we're going to do is simply, as I said, change a bit the notation. So from groups, we now go to features, okay, or rather feature maps, in the sense of kernels. Okay? So let's do it. Given x, I called xj the part corresponding to the first group, okay? Let me just define a feature map phi j that is giving me exactly this. So taking a vector, return its part, okay? So phi j goes from where to where? I need you to be awake and answer me, because it's going to be boring, and if I lost you, there's no sense in it. From what? Yeah, Rn something close. So let's call it x just to be sure, or whatever. Or I call it Rd before, if you want. Okay. In general, it can be any space x into what? R, exactly what you said. Rdj. Okay. This is going to be from j from 1 to g. Okay. Okay. Now, that's it. Okay. I just changed the name. Instead of a part, I call it a feature map. And that's what I did. Suppose that now you define the function fjx to just be the function that given a vector in Rdj and given the piece, return that function, the linear function on that piece. Okay? You agree that because I changed the notation now, and notice if you want that this is a feature map, a feature space fj, okay? So this means that now I can do this. You agree? Again, I already changed the notations here, I'm just repeating it. But if you remember from the theory of reproducing kernel Hilbert spaces, if this is a feature map and I define a function this way, you can tell me in which, well, I can tell you that it belongs to a reproducing kernel Hilbert space, and you can tell me what's the kernel. Fj. So if this is true, then Fj belongs to a reproducing kernel Hilbert space Hj. What is the kernel? If I give a feature map phi j, how do you build the kernel associated to this feature map? It's going to be a function kj equal to what? Just the inner product of the feature maps. Okay? And if you want, I could write here that I'm just taking the pieces of vectors and multiplying them, but that's not important. Okay? So this is the first fact. Okay? This is the second fact. Agree? So I'm going to change notation for another bit, okay? But let me tell you where I want to go. At some point, I'm going to say that everything works even if I drop this one line and I take an arbitrary feature map. So throughout now, we're just going to change notation and think that the feature map we're working on are exactly these guys. But at some point, we're going to say, what if I just delete this one line and I say that I had a very generic feature map? Or even more, I just had a kernel, kj. Can I still write an algorithm that looks like this? Okay, that's where I want to get to. Okay, but this is going to cost me another 5 minutes of changing the notation. So step 1, step 2. Notice that the map that associates wj to fj is by definition one-to-one. And so I have that I can define the norm that I also have this equality. Okay? So now we're working just in components. But let's define a big feature map, which is now a function not, it's a function defined by all the feature map at once. And so to do that, so basically what I want to do is that, okay, fine, here I'm just giving you a piece. But the function I was looking at usually was a function like this, right? For the sake of simplicity, let's assume that the groups are not overlapping for now. Otherwise, we have to, fumble around with the inf like we did before, like the min width like we did before. Then you agree that this one now I can write like this. Okay? I haven't changed the notation yet. Let's change the notation together. How can I write this? This is equal to what? A what? No yet. Well, this is going to be sum j from 1 to g, w j. For now, let's just do this, right? But this is what? How did I call this? fj x. Okay? So the f I'm looking for are sum of fj. Each fj belongs to a reproducing kernel Hilbert space defined by this feature map through this kernel kj. Okay? Question. Does f belong itself to a reproducing kernel Hilbert space? Yes. No. Say? What do you say? Yeah, so what he said is that I have to take the direct sum of the group-specific feature maps. And somebody else said that it's a sum of positive definite function, and they're actually both statements are correct. So we want to do exactly this. So again, somebody said, if I look at this, what I should do is I should define a vector W, which is the concatenation of all these guys, and a vector which is the concatenation of all this. Notice that in this case where you have no overlap, this is just X itself. No? I'm just concatenating. The phi that I obtained goes from RD to, say, in the simple case with no overlap, RD. In the case where I have overlap, I have to do this disambiguation by replication if you want. Okay? And how does it look like? As somebody said, this is just what? If I give you phi1, phi g, this is going to be what? How can I write this using the phi1, phi g? Think about it. If I sum them, phi1, phi g are of different size. So if I sum it, I just have to concatenate them. Okay? If you want, if you put here, you see it maybe better. Phi x, phi g. So I have to concatenate the feature vector, one after the other. Okay? So the feature space is the product of the feature spaces. What about the kernel? Well, somebody said that the kernel is a sum. Let's just write it. Well, if I take that feature map and I want to define this kernel, this is just going to be like this. But how much is this? Well, same as before, right? So I can take each of these guys that are now defined this way. So I have to do the inner product between the first part and the first part, the second part and the second part, and keep on going. So here I would get exactly sum. Well, let me just keep one. Sum of kj for j that goes from 1 to g, where kj I define it here. Okay? So far, so good? So we mostly change notation for now. Okay? We discovered that I could, if I want, think of the norm I've been using so far as a norm in a feature space, in a kernel space, where the kernel is just the simple kernel, which is the linear kernel. I didn't write it. Let me write it here on the parts. Okay? Okay, fair enough. Suppose that you really care of change notation a bit more. Okay? And what you want to do is you want to use this notation for kj. So here is actually good news. This class is too big. I don't want to delete this, and I don't want to delete this, I don't want to delete this. So notice what I call W, I can call F now through that identification, because W and F are related one to each other. So basically now I can just do this. H is the full space, and R is what? Is the sum of the norm of the pieces. But as you see there, the sum of the coefficients, the norm of the coefficients is equal to what? It's just the sum of Fj in Hj. Okay? And if you want, let's do it as we did it before. By the same argument we used before, you can just say that you're now looking at this minimization. Okay? You have a function which is a sum of functions, and for the function, you're going to penalize its norm. Again, I did nothing up to now. I just took the group lasso with no overlap. I changed notation, and I just rewrote the problem. And what I call W is now called W1, sorry, what I call W, I'll call F, and what I call W, F1, and so on and so forth. Okay? Now, suppose that now if you are in the case where you have the feature map defined this way, you're good to go. But if you just go in and delete this line, this line, this line, this line, and maybe that's it for now, which is where I gave a specific definition of phi j, everything works fine. This is just a generalization of a feature, of group lasso, where instead of getting groups, I define feature maps. So instead of defining groups, I have a feature 1, a feature 2, a feature 3. I have G feature maps rather than 1. And I want to, in some sense, combine them. Okay? And I want to try to select feature maps now, instead of selecting groups. So we could stop here, unless you want to use kernels. Why? Well, suppose that you do have feature maps, and the feature maps are each one finite dimensional. Okay? Then nothing. You can just you do this, and that's it. I chose in a perverse way to call F WF. Okay? But other than that, I did not do anything. But suppose now I tell you that I want to use two feature maps, and here they are. Is the feature map associated with a Gaussian kernel with sigma big, and the Gaussian kernel associated with a Gaussian kernel with sigma small. What's the problem? Well, they're infinite dimensional. So W, you cannot fit in the computer. So this equation here, you just cannot write. Okay? So what you could hope, look at that. So usually when you have kernels, okay, you have the hope to be able to solve the problem even if the kernel induces an infinite dimensional space, so a truly non-parametric setting, and the we called what? The representer theorem, right? Was that one thing that said that we were lucky and the W's we were looking at, potentially infinite dimensional, could actually be written as combination of kernel functions at points. Well, it's an exercise of one line to prove that indeed the F1, Fg that satisfy this equation, not for the phi j defined there, but for any phi j, for any kernel, can actually be written like this. Okay, so you have a representer theorem per component, which means that now instead of g vectors of size d1, dg, that now can be infinite, you now have g vectors, each one of size n. Okay, so the component j, each component j is going to cost you computing n coefficients. Okay, and this is independent on the size of the there. How do you compute the Cj? Because that's the last question. And I realize now that I forgot to check this part of the update. So I'll tell you the part which I'm sure about, and then we try to interpolate on the part that I'm less sure about. So there's going to be a prox. It is essentially going to be written on the C. So let me call now the notation. So let me. Sorry, this is super confusing. Okay, so let me call I is the number of point and J is the number of things. So let me call J I. Okay, now the notation is a bit better. So for each function j, I have to compute not one but n coefficients. And I want to write down the prox for one of the set of coefficients corresponding to the jth component. Okay? So let me first write the part that I'm sure about. The first I'm sure about is this one. That you have to replace this condition with this condition here on the norms. But the good news is that now you can compute the norm even if this vector of W is infinite dimensional. Because the norm now has, the function fj now has this representation. So we know by all the stuff we did on regularization networks, ridge regression, SVM, logistics, that the moment you have the representative theorem, you know how to compute a norm. Do you remember how it looks like, roughly? This kernel, I give you these coefficients. How does this look like? Well, you have to take the coefficient j, say transpose, take the kernel matrix j, the one, and then do this and take the square root. Okay? Now this is the part that this is also part that I remember. This part is, well, my guess is that it should be like this, so it should be equal to the other one, okay? But let me put it in, I believe it's like this, but let me check because I literally forgot to look it up. I think it's the obvious thing, but let me look it up. If it's not like this, it's almost like this, okay? So let's recap, okay? We spent 20 minutes changing notation. We said, whenever you see xj, put phi j. Whenever you saw fwj, put fj. Okay, pretty much. And just realize that you are working with these kernels. We go all the way down, and we decide that we can work either with the feature map explicitly, if we can, or with. At this point, we stop and I say, what if, as I told you already once, the feature map were not defined by groups of features, but were arbitrary feature map? Well, the math will go through. Anything will be well defined. The interpretation will be completely different. We will not be selecting group of features, but we'll be working with many feature maps, and we'll try to select feature maps. Or if you want, in other words, we're going to say that you see it from there, that our function is not given by one kernel, but is actually given by a sum of kernels. And what we're trying to do is to find which kernels are important. So if a kernel is important, it means that I'm going to update its coefficients. If a kernel is not important, after a while, the corresponding norm is going to be, small, and hopefully I can get rid of the kernel. So each kernel counts as much as this norm. Okay? So in the last 10 minutes, does it make sense? So it's a bit of magic, and the part which there is a part which is boring and a part which is a bit more magical. Okay, the part which is boring, you just change notation for a while and do obvious thing. Then you have to just take a step back, delete 3 lines, and realize that everything works fine, and you actually replace groups with kernels, and that's it. You actually have to do one more step proving the representative theorem, which I skipped because it's literally nothing. I mean, it's super easy. It's the same as the classical one. And then at that point, you're good to go. You can just go in and start. Does it make sense? With this little change of notation, we actually gained quite a bit, because we were working with just one kernel for a while, and now we know that we can combine kernels. Okay? I want to make one more mathematical statement, so to say, and then a few comments. Okay? So the mathematical statement is more a comment, which is, we already discussed sum of kernels, right? We said that every kernel, if you give me a bunch of kernels, I can sum them up and it's a kernel. So suppose that I didn't tell you this stuff, but I gave you 3 kernels, and I tell you use them. What would you have done? You sum them up, you obtain a new kernel, and you use it, right? Say in an SVM or anything like that, least squares. What's the difference between that thing and this? Absolutely, okay? Exactly. Write it at least once. The natural norm. The natural norm associated to the kernel which is the sum of kernels, is not this one. Okay, this one, if you want, it's a norm on F. Some norm B, I call it B. But there is also norm H, okay, associated to it, which is the natural norm. If I give you this kernel, there is a natural norm associated to this, which is the one whose square I given by the square of this component. Okay, this is easy to see. If I give you a space of functions which are given by the sum of kernels, I have a natural norm, an inner product, and everything. And then you can define also another one. Not unlike when I give you vectors, you can find L2 norm, which is the one that comes from the Euclidean inner product. You can find something else. Okay. So if you do this, notice that the problem becomes you don't have to do iteration. You have a closed form solution and so on. What do you lose? Well, exactly what I've been discussing for 4 days: sparsity. You're not going to select any of those kernels. You're going to just put them all together. Notice that, in fact, rather than, instead of having G vector of coefficients, you're just going to have one because you have one kernel. And that's what you estimate. So you reduce the complexity of the problem horribly, but you're going to take all the kernels. Okay? That make sense? So now I give you these two algorithms. Okay? We start from group last, so we discuss about sparsity. We're kind of excited because now we extended through a 20 minutes change of notation procedure sparsity from parametric models, linear models that we've been discussing for 3 days, to non-parametric models defined by kernel that we've been discussing for another couple of weeks. Okay? Let's stop a second and compare these two techniques. The one where you take a sum of kernels and you try to select them, and the one where you take a sum of kernels and you just put them all together and use them. Computationally, we already compared them. This one is much more complicated than this one. One is a linear system where you collapse everything, you just one set of coefficients. The other one, you have to run an iteration where you have many, many sets of coefficients. Okay? Let's just take a step back and think about a modeling perspective. When would you use techniques like this, where you're using, a sum of kernels? And when would you rather use this or this? So first question is, when do you think it's nice to use more than one kernel? What comes to mind? Well, there is an obvious one, which is, well, you want to use more than one kernel. Okay? You want, instead of just one kernel, you say, I want to use the polynomial and Gaussian and the linear, and try to hopefully get the best of each of them. Okay? So you want to augment the power of your algorithm. Instead of like picking the best kernel, you want to combine the kernels. You want instead of model selection, you want to do model aggregation. Say, this is one way of doing it. If you do it like this, you're assuming that some model is important, some other is not. So you try to depress it. Otherwise, you just try to mix them. Okay. What else? What would you think could be interesting to use not one but many kernels?
When you say like using different kernels, are we talking about, for example, using it on the same data set? Or
Yeah.
different?
You can have some features that are different data types, like strings versus floating point numbers that you can't.
For example. Yeah, you can do, so what he said is you can give different data features. There are very different kinds, okay? So you have, you say you have an image, and then you have some text, and this is what you want to represent, and you can represent the words and the pixels. Or you have an image, and you want to consider color histograms, but also edges histogram, okay? So you literally have a list of numbers that make perfect sense, but they're not easy to compare, mixing them up. So you want to take, say, the strings, the words, and the pixels, or the edges and the colors. And each of them is going to define a different kernel. So if you want, I guess there's some form of data fusion, I guess is one term you can use. So you have different sources for the same data, and you want to fuse them. And you do it at the feature level. And there again, you can say, well, to me at least, if you give me two features, okay, I them. If you give me 2 kernels, I'm just fine combining them. If you give me 1,000 kernels or 1,000 different set of features, then maybe it would be a good thing to try to select the ones that are important, okay? These are completely 2 different priors, so my comment is super sloppy. It's very practical, okay? It also comes from the fact that people actually look at this stuff quite a lot, and at the beginning, the idea was, wow, this is amazing because this is selecting the kernels, and then what you see is that, in fact, these actually work pretty well if you're just looking at pure prediction, okay? Just estimating f of x to make prediction. This is not unlike when you compare L2 and L1. L2 doesn't really work bad if you're looking for prediction, just is completely unable to provide interpretable model because that's not what it's tailored for. So in a lot of different problems, just summing up kernels and using this, if all you care about is prediction, is fine. If you try to actually, if you really care about selection, then maybe doing something like this is, and I can think at least of one situation where actually this is actually super nice. Suppose that you want to do nonlinear variable selection. This is our last bit of information about for lecture sparsity. How would you do it if I give you this algorithm? Variable selection, okay, which we've done so far by writing a linear model and then try to delete the coefficient of the linear model. Now I want to do it nonlinearly. So I want to allow myself some form of nonlinearity in my model, some form of, because one thing that nobody complained, but it's a fairly obvious complaint, is what if sparsity, but my model doesn't depend linearly on my features, my variables? What would I do? Well, now I give you this algorithm. What would you do? Yeah.
You could have a nonlinear feature map and get the corresponding kernel map.
Yeah, but that's what we've done. You have to be a bit more precise than that because that's anything, right? Anything is like that. You give me a nonlinear feature map. What, a nonlinear feature map on what? If you want to do nonlinear variable selection.
On the variable system.
On?
Like you just, whatever nonlinearity you want to get on that variable, use that as the feature map.
On just that variable. Okay, so the important thing would be essentially to say, take a kernel, and now here take xj, where this is just looking at the component j of the vector. Okay? Means that the function fj is actually just a function of the component j. Okay? So I want to stop here. But so just think about this, okay? This is the case where you attach a kernel to each real variable, to each individual feature, okay? And then by selecting the kernel, you're selecting the variable. The interaction among variables is still going to be linear because you're just summing up, but the interaction of the output to the variable is nonlinear. Okay? So think a bit about this and just think, just to, I'm actually going to ask this question. I'm not going to be around next week, so I can ask this question in 10 days. But think, what would you do if you want to try to start to put interaction about more than one variable? Okay? So again, the point I wanted to make here is that this stuff, this is sometimes called L2 multiple kernel learning. This is called L1 multiple kernel learning. And the message I want to give you is that somehow this one seems to be more important when you want to do selection. And at least one case where I can see that this is very important, if you want to try to do some kind of nonlinear extension to L1, where each function, the output depends nonlinearly to each individual variable, and then you just sum them up. Okay. So this is the last class on sparsity. Next week there's going to be a bit of a statistical learning theory interlude. We're going to talk about stability. And then this is going to be Charlie giving you class. And then I'll come back in 10 days, and we're going to move on with more algorithm. We're going to discuss online, manifold, multitask, and blah, blah, blah.